All right, so 3.4, it's called zeros of polynomial functions. Zeros is another word for roots, which also is another word for solutions. So if you've never seen root before used in that fashion, I know you've seen solutions. So zeros, root, solutions mean the same thing. All right. So the first thing we're looking at this section is the rational zero theorem. So in order to find all possible rational zeros, you would do plus or minus the factors of your constant over the factors of your leading coefficient. So that plus or minus is assigned to each one. And you'll see what I mean in a second. Okay. All right. So where that comes from, if you look at this right here, if we had just a simple linear equation of 2x plus 3 equal to 0, our constant is 3, our leading coefficient is 2. So notice what we have here is the constant over the leading coefficient, which is the solution. So that's where this comes from. You're talking about all of your possible solutions. You would have your factors of your constant over the factors of your leading coefficient. All right, so let's see how this works. All right, so list all possible rational zeros of f of x equal to 15x cubed plus 14x squared minus 3x minus 2. So notice what we did. The first thing we did was establish what our constant. Your constant is always the number that has no variable attached to it at all. Your leading coefficient is the number that's attached to the variable with the highest exponent. So see, 2 is our constant, 15 is our leading coefficient. Factors of 2, 1 times 2. Factors of 15, 1 times 15 and 3 times 5. Before we go any further, is everybody all right? Once again, your constant is the number that's not attached to a variable at all. Your leading coefficient is the number that's attached to the variable with the highest exponent. Then we have the factors of 2. And so we're going to take the factors of 2 and place it over each one of the factors of 15. And that's what I did right here. You got 1 over 1, 1 over 15, 1 over 3, 1 over 5. Then 2 over 1, 2 over 15, 2 over 3, and 2 over 5. And this plus or minus is attached to each one of those. I just put it in the front, but it goes to each one. So when you look at this, we have 1, 2, 3, 4. We have 8 specific numbers, but then if you apply the plus or minus, that means we have 16 possible rational zeros. And then, of course, you simplify the list. 1 over 1 is just 1. 1 over 15 is the same. 2 over 1 is just 2. So this would be a most simplified list. So now it is possible to have repeated values in certain lists. So, of course, you want to repeat the values. And we'll see that in the next example. So now this doesn't give you your solutions. It gives you your possible solutions. And so you'll see what we would do with that as we progress in this section. But it gives you all of your possible rational solutions. Doesn't include imaginaries, possible imaginaries. So, all right. Any questions on this before we scroll up and do it again? All right. So let's look at this one right here. 4x to the 5th plus 12x to the 4th minus x minus 6. We see that our constant is 6 and our leading coefficient is 4. Factors of 6, 1 times 6, 2 times 3. Factors of 4, 1 times 4, 2 times 2. Don't have to use the 2 more than once. So we'll place our factors of 6, the constant, over the factors of our leading coefficient. It comes here. Let me erase this. So this is our list now. You take 1, place it over 1, place it over 4, place it over 2. Then we do 6 over 1, 6 over 4, 6 over 2, 2 over 1, 2 over 4, 2 over 2, and then 3 over 1, 3 over 4, 3 over 2. All right, questions. So now we simplify the list, and we'll see that some values will cancel out or be repeated, so we don't have to rewrite them. That 2 over 4 is the same thing as 1 over 2, so we don't have to repeat that. 2 over 2 is the same thing as 1. We already had that. 3 over 1, excuse me, is 3, and that appeared here. 6 over 2. 3/4 is not repeated, but 3 over 2 is repeated right here in 6/4. So you simplify and then make sure you don't have any repeated solutions. All right, any questions? All right, so let's use that. So we have x cubed plus 7x squared plus 11x minus 3. They want us to find all zeros. So now notice they didn't say find the possible zeros or the possible solutions. They want us to actually find the actual solutions. All right, so we take our factors of 3, place it over our factors of 1. So that's what I did right here in the purple. Found my possible solutions. So I took 1, placed over 1, and then 3, placed over 1. And so right here we have 4 possible solutions, plus or minus 1, plus or minus 3. Also keep in mind that this is 3 right here, so that lets us know we can get 3 solutions. Any problems so far? All right, so let's use synthetic division to see which is a solution. Remember, these are our options. Positive 1, negative 1, positive 3, and negative 3. So when we do synthetic division, don't forget, in order for it to be a solution or 0, that means we have to get 0 as our final part of our answer. That's our remainder. Our remainder has to be 0. So use 1 first, and that's what I put right here. Coefficients 1, 7, 11, and negative 3. Got those from right here. 1, 7, 11, and negative 3. Bring down 1. 1 times 1 is 1. 7 plus 1 is 8. 1 times 8 is 8. 11 plus 8 is 19. 1 times 19 is 19. And add those together, negative 3 and 19, I get 16. So don't forget we need 0 here. in order for it to be a solution. So 1 is not a solution. And so you would go through this process of checking to see which one of these, or if any, would be a solution for us. Do the same thing for -1. Start off with -1 right here in our box. 1, 7, 11, and -3 still our coefficients. Break down +1. 1 times -1 is -1. And you just keep following that process, and you see we get -8 as our remainder. All right. +3. Follow the same process, but this time notice we get 120 as a remainder. And if we do -3 though, notice we get 0. And that's what we needed to prove that we have a solution. So -3 would be one of our solutions. So any questions before we go any further? Very good. All right. So -3 is one of our solutions. Remember, we should be getting 3 of them. So that rational theorem, possible rational theorem, only give you the rationals. So if there's an irrational solution or if there's an imaginary number as a solution, you won't get it out of that. So what we're going to have to do now is take the remainder of that equation, or that remainder of that function, x squared plus 4x minus 1. Remember last class, remember we used synthetic division to break down our functions. So that's what we have right here, x squared plus 4x minus 1. We cannot factor it, so we use the quadratic formula. Also, don't forget that this right here starts with x squared because our original function has x cubed. So you always start one exponent or 1 degree less than what you originally had. So that's why we started with x cubed. So x cubed plus 4x, x squared, excuse me, plus 4x minus 1 cannot be factored. So we use the quadratic formula. A is 1, B is 4, C is -1. Plug those in here accordingly. So that's -4 plus or minus square root of 4 squared minus 4 times 1 times -1 all over 2 times 1. Simplify what's under the radical. 16 plus 4, which would be 20. That square root of 20 can be broken up to 4 times 5, taking the square root of 4. Here's 2. So that's why we have 2 square root of 5. So that'd be -4 plus or minus 2 square root of 5 over 2. To simplify further, we see that the 2 can divide into the 4 and divide into the 2 and leave us with -2 plus or minus square root of 5 as our other 2 solutions. And so don't forget, if it asks for all solutions, you have to give all 3. -3, then -2 plus square root of 5, and then -2 minus square root of 5. All right. questions? Any questions? All right, can I scroll up? Very good.
Oh no, just stay there.
All right. All right, so the next thing we have is complex conjugate theorem.
Thank you.
Yep, not a problem, not a problem. If a plus bi is a solution of f of x, then a minus bi is also a solution of the function. So that's our complex conjugate theorem. So if you know, in other words, let's look at what we have here. We're talking about the conjugate. The conjugate is just the changing of the sign of your imaginary part. So if you know you have 4 plus 5i as a solution, that means 4 minus 5i is also a solution. That always is the case. They don't come alone. So if you have an imaginary number, just know its conjugate is also a solution. If you have an imaginary number as a solution, its conjugate is also a solution. So negative 2 plus 7i means negative 2 minus 7i is a solution. Negative 8i and positive 8i is also a solution. All right. All right, so let's look at this next example. Find a fourth degree polynomial function with real coefficients that has negative 2, 2, and 1 as zeros, and such that 4, 3 is equal to negative 150. All right, so normally what we have is that we have an equation or we have a function and we know what are the solutions. This time they give us the solutions and then ask us what's the function that gave us that those solutions. So we're working in reverse. So I want you to keep that in mind as we continue to progress forward. We are working in reverse. They give us the solutions and they want to know what function gives us these solutions with this initial condition right here. Oh, my eraser is still on. With this initial condition that when you plug in 3 into the function, you get out negative 150. All right. So we have 3 solutions. They give us 3 solutions, negative 2, 2, and I. And they want to know what function will give us these 3 solutions. And when you plug 3 into the function, you get out negative 150. All right. And that's what I just said right here in the green. They give the solutions and want to know what function produced the solutions. So just make sure we understand what they're asking for when you see this type of set of instructions. I'll scroll up right here. All right, so notice they gave us 3 solutions, but they want a 4th degree polynomial. 4th degree means that the highest exponent of your polynomial is 4. So that means we should be getting 4 solutions, but they only gave us 3. We just talked about the complex conjugate theorem. They gave us an imaginary solution. So that means when they give you I, they assume you know that another imaginary number comes with it, and that's going to be negative I. That's what we have right here. The complex conjugate theorem says that if I is a solution, that means negative I is a solution. So remember the complex, well, your conjugate is just when you change the sign of your imaginary part. So all we had was I here, so that means negative I would be a solution as well. All right, so how we're going to set this up, let me erase this just so that we can get clarity. I'll put it back in a second. Just wants to see this. So if x equal to negative, well, if my solution is -2, in order for that to be the case, then that means this had to occur. X plus 2 was equal to 0. So remember, we're working in reverse. So I need to take that -2 back over in order for me to have x plus 2. I need to use the opposite of each one of these symbols right here. So the way I'll set it up is this way. I will have x minus -2, x minus 2, x minus I, and x minus -I, which will represent those solutions, okay? X minus -2, x minus 2, x minus I, x minus -I. All right, remember we're working in reverse, and we need to produce the opposite in order to be able to get those solutions. All right. Any problems with the setup? Also, we put an A out front to represent a possible coefficient that we will be using in the future. So you put an A out front. We don't know if we're going to need it, but right now we just put a variable out there to represent a possible number that will be multiplied to our function. That'll come into play later, where you do put a variable out there to represent that. And you don't want to use X because or Y, because that's what we normally use just as our variables. Remember, f of X is equal to Y, and we have X in our function already. So you use something other than those two. Normally we use A. All right, so what that then does is gives us this when we go to simplify. X plus 2, x minus 2, x minus I, and x plus I. All right, so what I would do is go ahead and multiply and distribute. I will multiply these two together and then multiply these two together because things are going to cancel for us. You'll see in a second if you haven't already got to that step. So you distribute x into the next parentheses, distribute 2. That'll give you this, x squared minus 2x plus 2x minus 4. Then distribute x and distribute -I, doing your binomial distribution. And so that will be your result. X squared minus 2x plus 2x minus 4 right here. And then x squared plus ix minus I squared. See that our middle terms will cancel in both cases. And also I squared is equal to -1. So here we have x squared minus 4 times x squared plus 1. Once again, do your binomial distribution. X to the 4th, x squared minus 4x squared minus 4. And our result is right here, x to the 4th minus 3x squared minus 4. So any questions before we see if we have a number for A? So all of this is algebraic. We're just doing algebra, just doing our distribution, combiner-like terms. Just have to make sure you're careful with your terms and careful with your signs. All right. So the last thing that we have is that initial condition of when I plug 3 into the function, I should get out -150. right. So we do that, plugging in -3. So it's -3 to the fourth minus 3 times 3 squared minus 4. And that is supposed to equal to -150. And that's where this a may come into play. We may need assistance from another number in order to make sure that occurs. So 3 to the fourth is 81. 3 squared is 9. 3 times 9 is 27. So you got 81 minus 27 minus 4, which will give me 50. So that leaves me with 50a equal to -150. Divide by 50, a is equal to -3. So to finish it off, plug in -3 for a, and then you distribute the -3 to each term. So our final function, or our final answer, our actual answer, is -3x to the fourth plus 9x squared plus 12. Any questions? Any questions? All right. Questions on that one before we do another one? Do another one. All right. Can I scroll up? All right. So doing the same thing. This time we have a third degree polynomial. They give us two solutions, -5 and 4 plus 3i. And when you plug in 2, you get 91. All right, so notice our solutions are here. That third one comes from the complex conjugate theorem. They gave us 4 plus 3i. So that means 4 minus 3i is also 1. Let me erase this. All right, so don't forget, in order for us to get the solutions, remember they give us solutions and we want the function that gave us those solutions. So we have to go in reverse. So if I had x equal to -5, that means I need at some point to have x plus 5 to figure out what function gave me that solution. So that's why we have x minus -5, which will ultimately give me that plus 5, x minus 4 plus 3i, then x minus 4 minus 3i. So when you do it that way, you set it up that way, that ensures that you're getting the opposite side of each one, or opposite sign of each one of your solutions. All right. Question before we go to
I
the
have a
next.
question. Is that a 91?
91. Yeah, f of 2 is equal to 91.
Okay, thank you.
Yeah, no problem. All right, next step is to simplify what we have. That negative to negative turns positive for that 5. Then we want to distribute the negative into both of our imaginary solutions. And that's what we have here. x plus 5, x minus 4 minus 3i, x minus 4 plus 3i. And once again, you want to go ahead and multiply these two together because those are the ones that have the conjugates involved. Want our imaginary part to cancel out. So it's easiest to go ahead and multiply those two together first, let the imaginary parts cancel, and then we'll be able to use just all real numbers. So that's all that will be left. So you distribute x into each term, distribute -4 to each term, distribute -3i to each term. And let me erase some of this so we can see what's going on here. All right. So we have this result right here. We have x squared minus 4x plus 3xi minus 4x plus 16 minus 12i minus 3xi plus 12i minus 9i squared. So, oh, didn't mean to do that. Yep, sorry. Let me go back down. Here we go. All right, so we have our terms, imaginary parts that cancel. 3xi, positive and negative 3xi will cancel. Positive and negative 12i will cancel. Then we have like terms in the 4x's that will cancel. I mean, not cancel, but combine to give us negative 8x. And then also I squared, don't forget, is -1. So that'll be a +9 in the back. All right, any questions? Here we have a 16 and +9. That gives us this +25 right here. So now we're here with x plus 5 times x squared minus 8x plus 25. So we'll distribute. And we have x cubed minus 8x squared plus 25x plus 5x squared minus 40x plus 125. Any problems? Any problems? Combine your like terms, 8x squared plus 5x squared, negative 8x squared, excuse me, plus 5x squared is negative 3x squared. And then 25x minus 40x is negative 15x. All right, so we have this as our most simplified expression up to this point. Now we need to see if anything needs to be here for a. So remember, when we plug 2 into our function, we're supposed to get out 91. So that's what we do right here. 2 cubed minus 3/2 squared minus 15 times 2 plus 125, and that's supposed to equal 91. Simplified, 2 cubed is 8. 2 squared is 4. So ultimately we'll have 8 minus 12 minus 30 plus 125. Ends up being 91. Divide both sides by 91. A is equal to +1. So if a is equal to 1, plug 1 in for a, and you know 1 times anything is itself, and this will be our answer. Questions, questions, questions. Oh, sorry about that. Didn't mean to do that. Okay. All right. So yeah, that's it for that. So we got 3, 5. What is 3, 6? Yeah, it's 11:46. I guess we can look at 3, 5. Let me do this real quick. Sit tight 1 second. All right. So looking at 3, 6, 3, 5. 3, 5 is, yeah, 3, 5 is short enough. We can do 3, 5. Looking at my math lab though, some of you guys really need to get with me about getting an extension on chapter 1 and chapter 2. Make sure you email me on that. Some people have requested. Just make sure you get with me because you don't want to get too far behind, and you don't want to have zeros. Don't want to have zeros if you're trying to pass the class. So make sure you guys get with me. Make sure you have chapter 1, chapter 2, access to chapter 1 and chapter 2. All right. So let's look at 3, 5. Rational functions and their graphs. So asymptotes are just places where the function is undefined or does not exist, or places where the graph does not cross. All right, there are 3 types of asymptotes. We have vertical asymptote, horizontal asymptote, and a slant or oblique asymptote. So let's look at the first one, vertical asymptote. So whether the denominator is equal to 0. So you will simplify as much as possible. I wrote as much twice. Nice. So simplify as much as possible. Then set the denominator equal to 0 and solve. All right. So find a vertical asymptote, if any. So when you talk about graphing, you have something like this. You have these imaginary lines that are right here where your graph will not cross. And so see that the graph does this, and then this graph right here does that. So that's what your asymptotes will do. Create these imaginary spaces where your graph will never cross. So there's nothing we can do as far as simplifying this expression. So you just go ahead and set the denominator equal to 0 and solve. So x squared minus 9 set it equal to 0. So x plus 3, x minus 3 if you decide to factor it by solving, or solving by factoring. And that'll give you x equal to negative 3 and x equal to 3. So we have two vertical asymptotes. All right, any problems with that? All right, so the next one we have x plus 3 over x squared minus 9. So notice the first thing we do is to simplify. You do that if you can. The first one we couldn't, and this one we can. We see that x plus 3 and x plus 3 will cancel once you actually factor out x squared minus 9 using different squares. So now that x plus 3 that cancels out in the problem, since it was in the denominator, we don't, ignore it. You can't just ignore that it was there. So it does produce a restricted value. So in other words, before we've had graphs when maybe you have a opening right there, like an open circle, that's the type of value it will produce. Like, so negative 3 would not be a value you could use here. So that you have the restrictor value, but it will not produce a vertical asymptote. The x minus 3, the part of it that's left will produce that vertical asymptote right here. So you set both of them equal to 0 and solve. So notice that x plus 3 produce a restricted value at negative 3, and then the x minus 3 produce a vertical asymptote at positive 3. So if it cancels out, it's going to produce a restricted value that your equation cannot use, but the actual vertical asymptote will be produced by whatever is left in your denominator. Any problems before we look at the next one? All right. So the next one, h of x is equal to x plus 3 over x squared plus 9. So cannot factor x squared plus 9. So if you decide to solve, I'll go ahead and set it equal to 0. Notice we get imaginary values. So it means there's no vertical asymptotes. All right. Questions on vertical asymptotes?
Hold on, just stay there. I gotta copy this.
Mm-hmm. All right. We good. We good. All right. We good. All right. So let's look at horizontal asymptotes. In this description of how you get your horizontal asymptotes, we're going to let n be the degree of the numerator, let m be the degree of the denominator. So in other words, when we say degree of the numerator, you're talking about the highest exponent in your numerator and the highest exponent in your denominator. This right here was just, that's not anything. I mentioned that before, that's nothing. Yeah. So we're looking at n being the highest exponent of your numerator, m being the highest exponent of your denominator. All right. So first condition, if n is less than m, then your horizontal asymptote is just 0. Y is equal to 0. Notice for the horizontal asymptotes, we use y. For the vertical asymptotes, we used x. So y is equal to 0. If n is equal to m, then you take the leading coefficient of the numerator, place it over the leading coefficient of your denominator. Once again, notice it says y equals. And then if n is greater than m, there is no horizontal asymptote. We will go to the slant asymptotes. Mhm. All right. First one is find the horizontal asymptote, if there is one. So they give us 4x over 2x squared plus 1. So remember, what dictates what we do is the exponents of our numerator and our denominator, degree of exponent of our numerator denominator. And so exponent, or the degree of our numerator, is 1. Degree of a denominator is 2. Remember, it's the highest exponent in your numerator and denominator. So n is equal to 1, m is equal to 2. N is less than m, so that means y is equal to 0. All right, next one. Here, highest exponent for each is 2. So since they are equal, we'll take the coefficient, 4 and 2. And so y is equal to 4 over 2, which is just 2. All right. Any problems? Any problems? And the last one like this. See that our numerator has a 3 as its degree. Denominator has 2. So n is greater than m, so it means no horizontal asymptote. All right. Question before we look at the last one. All right. So slant asymptotes. So when n is greater than m, there should be a slant asymptote. We would just use long division or synthetic division if possible to find. So your slant asymptote will be the quotient. I scroll up. Okay, so want to find a slant asymptote. Notice that 2 is greater than the 1 that's down here for our exponent. So that means we would find the slant asymptote. And because of the way that our denominator is set up, we can use synthetic division. That's what I did here. So use your opposite sign. Use 1, -4, and -5 for your coefficients. Bring down 1. 3 times 1 is 3. -4 plus 3 is -1. 3 times -1 is -3. Add -5 and -3, you get -8 as your remainder. So you set up your answer that way. Maybe start off with 1 less degree than what you originally had. And the x minus 1, this part right here, is your slant asymptote. The remainder is not a part of that. Questions? Any questions? All right, got one more. Okay, before scroll up. Okay, so same type of deal with g of x. We have x squared plus 1 over x minus 1. I decided to use synthetic division again, because what we have right here, we have x minus 1. Use the opposite, which is positive 1. We had a missing term. Our x term is missing, so I use 0 as a placeholder. And just perform synthetic division. Bring down your 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1 once again, and then 1 plus 1 is 2. Gives me a remainder of 2. X plus 1 will be the slant asymptote. All right, any questions? All right, is everybody good? Everybody straight? Okay, so that's 3, 4, and 3, 5. As always, try the stuff out. See if you get stuck. If you have any questions, feel free to ask them. And we can knock those out. Shoot me that email. Other than that, I will see you guys on next class. Have a good, yep.
I'm sorry, can you go back before the asymptotes? I didn't write something down. So.
Okay, not a problem. Let me know when to stop. Oh, you said before the asymptotes?
Yeah.
Okay, so you're talking about 3.4. Okay.
Yes, please.
So this is 3.4. Let me know where to go. Keep scrolling up.
Oh, I'm sorry. Just stay there.
Right now. Okay.
Let me see. What's the one? Yeah, it's where the 91 is. Can you go a little bit down? Let's see. Yeah, right there.
Okay. Hold up, hold up.
Can you go down? Okay, thank you.
All right, not a problem. Not a problem. All right. See anybody else? Anybody else before we close? Everybody good? All right, you guys have a good one. I'll see you on Wednesday. Take care.